So thank you, everybody. Much like everybody else, I have 20 minutes and a lot to get through. I also realize I'm the last speaker for the day, so I'm standing between you and food or beer. So I'll try to get through it pretty quickly here. So indirect time of flight, I believe my counterpart from IDS did a really good job of explaining it in the time that he had. But there's a lot of applications for indirect time of flight, everywhere from robotics to different types of machine vision, whether that be food inspection, factory automation. Scanning, ironically, is an area. Everybody's gone through a self-checkout at your local convenience store. That's scanning a barcode, but loss prevention is a big thing. There's actually a lot of theft on that. So you're consistently trying to get more information. Depth is one thing that you can kind of cross-reference with the barcode in case somebody's switching a barcode out from an expensive item to a cheaper item. And all sorts of different other mapping applications, so on and so forth. So it really is a great technology, but having said that, there are a lot of limitations within the technology that is keeping it from being more widely adopted. And so I'll talk about in this presentation some of the ways that we believe we're able to mitigate that. All right, so first things first, again, I know that you sat through a presentation where IDS actually did a really good job of explaining indirect time of flight. But basically, it's pretty much your standard CMOS image sensor. You send out an illumination, of course. It bounces back, and it's going to come back at a different phase from when it was sent. So effectively, the delta in the phase is how we're able to calculate distance. And that's at a very high simplistic level of indirect time of flight. Direct time of flight is more where you're actually measuring the time. So this is not that, again, this is more based on a phase concept. So really, I mentioned again that there are some limitations within iToF that are keeping it from being widely adopted. So the first, and I think probably one of the more important ones, is motion. And I'll talk about why motion is a difficulty for iToF and some of the things that we're able to do to allow us to gather depth information with iToF that has motion. The second is accuracy and resolution. I'll talk a little bit more about that when we get there. One of the key items here is the distance at which you're able to detect with some accuracy. Especially outdoors, it's pretty difficult. A lot of this technology relies on either LEDs or VCSELs, and these are at the 850, 940 type nanometer wavelength. That's a wavelength that has a lot of sunlight, sends out a lot of that. Indoors, a lot of ambient light. So you're consistently dealing with noise from either the sun or from ambient light sources. And that's one thing that really makes distance a difficult thing to do with iToF. And then the last but not least there is the overall system cost and space. I'll talk about this again a little bit more, but on the system cost and space side of things, with indirect time of flight, you're calculating distance basically on many different phases. So for every single pixel of data, you could have 4 to 8 different calculations that you need. And that's really data intensive on the processors that are out there. In fact, there are not many processors that I'm aware of that can even do above VGA type resolution. So it's really data intensive. So what happens is then there tends to be a discrete component, and all that component is really doing is just actually calculating depth. So either you have a really, really high-end processor or FPGA, quite expensive, or you have a discrete component which sole purpose is literally to do the depth algorithm. So from a system cost and space perspective, there's some limitations currently with iToF. All right, so the first item that I talked about here is dealing with motion artifacts. So if you take a look at the top picture there, this is just somebody tossing a tennis ball up in the air. And this was taken with a traditional iToF camera. And as you can see, there are artifacts that are related to the motion. Now, the reason that this is happening is much like I said, you are taking many different phases between, let's say, 0, 90, 180, 270. You're taking all of these different phases and you're calculating depth. Now, as I'd mentioned, you have to output that to either an external discrete processor, or you have to output that to a SoC, a large SoC. In the process of doing that, you are reading that out every time. So you've got a phase, you're reading it out, you've got a phase, you're reading it out, you've got a phase, you're reading it out. All of that takes a lot of time. It sits into a processor's memory, and then the calculations happen. And so therefore, it presents a really difficult challenge for you if you want to deal with motion. Because any motion in between that time that you're reading it out and the process is happening, you're going to create artifacts. So a more optimal way of doing this would be you take the different phases, you store them locally, and then after you store them locally, you also process them locally. So this is really kind of the key solution to dealing with motion artifacts. It's the local storage of the different phases, and it's the real-time calculation, ideally maybe even on the sensor, that is going to reduce your motion. And so IDS actually has a great demo over there where they have a fan that's spinning, and they're doing that with indirect time of flight. We actually have a booth over in the 10 hall. You're more than welcome to stop by, but we also have an iToF demo too with a little conveyor belt that we're doing depth with motion. So this is a key one, right? And think about all the applications that I mentioned. You can't just sit there on a visual inspection line. You see an apple, it's got a dent in it. Okay, you stop it because you can't deal with motion. You stop it, you determine that there's a issue or a defect, and you throw it out. Well, okay, in that time, right, you stopped completely your entire inspection line. So you just lost efficiency. You're trying to scan an object, but it takes 2 or 3 times to do it because there's motion. You're losing efficiency. So I think this is really one of the biggest critical limitations of indirect time of flight. And I'm not sure if this is going to play a video. I'm hoping that the video plays. Let's see. Okay, so the video is actually going to play. So on the left there is a smart iToF device from onsemi. On the right is our competition. But what you can see happening there is effectively what I described. You have a very fast moving spinning wheel with objects on it. And of course on the left there, we're using our smart iToF. On the right is a competing solution that is using that more traditional architecture. So here in this case, right, obviously it's not a reliable calculator of depth. All right, the second thing too is about the accuracy and the resolution. So the highest resolution, and IDS mentioned this as well, is 1.2 megapixels. Now the reason that the resolutions had been limited to VGA is for exactly everything that I just said earlier, that processing depth is very, very data intensive. There's only one SoC that I know of right now that's not a super high-end SoC that's even able to do the depth calculations, and they're doing it at VGA. So the resolution actually is oftentimes limited by the processing element. So obviously, though, at longer distances and even at shorter distances, the more resolution you have, the more accuracy you're going to get. The other thing I'll note here, too, is that these are running off of VCSELs that are at 850, 940 nanometer. So your quantum efficiency should be high for that. In the case of our particular iToF device, we're achieving over 40% quantum efficiency at that level. So again, when I'm talking about you need to block out ambient noise, the more sensitivity that you have, the more that you're able to align with the VCSEL, the more it's going to block out all of the ambient light from either the sun or from other light sources. And this is actually just speaking to an example of that. So here we have a board of different lengths and steps. And it's the range at which we're actually imaging here is at 75 centimeters. And we're able to detect 1 millimeter difference between those steps. So that's about a 0.1% accuracy, highly accurate. Again, using alternate solutions, accuracy even at short distances is actually something that's pretty difficult here. So this is a pretty large achievement for us. Now, what's kind of making the magic behind the distance detection and some of the things that I've mentioned here? Now, your traditional iToF has either one or two different types of operations. So you have what we could call like a continuous wave operation or phased iToF, where you have a continuous signal coming out of the VCSEL, and then the sensor, in a rolling shutter sensor, because you're exposing one row at a time, and then you're going row readout, all the way through the sensor. That means that the sensor is exposing basically during the entire time of that continuous wave. Well, now as a process of that, all of that ambient light that you have in the sunlight, that's just giving it more time to introduce noise into the image. Okay, so the alternate to that, though, is you have some sort of pulsed global shutter type operation. And so there you have basically a single short burst of an LED or a VCSEL. And in that case, right, you do need a global shutter architecture because you need all of the pixel array to be exposing in exactly the same time. And then when that happens, right, we get the modulation and then we deliver a response. Now, the best of both worlds would be really to do both here. So if you have a global shutter sensor, you send out a very short burst of light, and that short burst of light really limits the amount of time that sunlight or ambient light can introduce noise in the NIR. The global shutter, as I'd mentioned, aligns to that VCSEL source, and then you still have the modulation, which is actually being done on the sensor. And so therefore the response is provided. So this is really kind of the key to how you're able to image with depth, far distances, and especially outdoor, because effectively the sensor is only exposing for a very short period of time, and then also for eye safety reasons, you don't want to burst that VCSEL at really high intensities for a long period of time, because people may not be able to actually see the 940 nanometer, but it certainly can affect your sight. So in this case, you can burst at really high intensity, but for a really short duty cycle, and in that case, you're eye safe. That high intensity, by the way, also at that very short duty cycle, also can help block out any sort of ambient noise. So this is really kind of the key. And you know, the chart there on the middle left really kind of explains, okay, here's the resolution that you have, and here's the distance that you can achieve. And for most iToF solutions, we're looking at the kind of 5 type meter range. For our smart iToF solutions, I'll show you some images here, but we can go all the way out even up to 30 meters. And of course, the direct time of flight is really where you go for very, very long distances. All right, so here's an example. So this is an image that we set up outside our office, and we had various different objects that are sitting outside. It's bright sunlight. This is in San Jose, California, so we have the California sun there. And as you can see, even out at 20 meters, we're accurately getting distance. The distance kind of scale there is at the bottom, between the red being close and the blue being further away. But you're seeing there that even at 20 meters, right, that we're able to get accurate distance outdoors, which is really impressive. If you're familiar, again, with the technology, the best you could probably do on prior technologies was something like maybe in the magnitude of 2 to 3 meters. And then similarly, even indoors, where you don't have sunlight, but you still have a little bit of IR content through ambient lighting, we can get all the way out to even 30 meters and plus with a highly accurate distance calculation. So I'll go over this one pretty quickly here in the sake of time. I do want to allow for questions. So this is where we're showing basically what is capable of being done, where you have direct sunlight on an actual driver, but because of the way in the operation of the actual sensor with the global shutter operation, you have a VCSEL that's very close to the person here. It's going to block out all of the sun if you're only aligning to when that VCSEL is on. And then finally, the last point for optimization here is on cost and system size. As I'd mentioned prior, again, many iToF devices, you need an external discrete component and memory in order to be able to calculate the depth. With the smart iToF solution, if you're actually able to calculate the depth real time on the sensor, obviously you don't need an external discrete component, and potentially you could get away with a lot lower cost FPGA or SoC. So this is a key one too as well for size and cost. So really quickly, with my short time left here, I just want to kind of describe the device. Again, you can see it over at the IDS booth, you can see it over at our booth in Hall 10, but really I believe that all of those limitations that were holding back iToF from being adopted, we've resolved in some form or fashion. The low motion artifact that I mentioned at the very top, the depth and the accuracy, the low system cost, the longer distance that I was talking about, and then last but not least, something that I didn't talk about, but we have a development environment that's very simple to use. We have a tool that we call DevWare. That DevWare allows you to do a lot of the calibration of the iToF on it, and it does have like a 3D point cloud and other types of looks. So from a development standpoint, we've tried to make it as easy as possible. The sensor itself is 1.2 megapixel, and it actually has the capability of doing dual frequency modulation. That's another thing that allows you to get more accurate a longer distance is dual frequency as well, because you're able to have shorter and longer wavelengths. Obviously, the longer getting the distance, the shorter getting more accuracy. So realistically, we believe that all of those, again, all of those items that were holding back this technology have been resolved. From a motion perspective, we have a solution. From an accuracy perspective, there's a solution. From a distance, we're now able to do more accurate distance at closer range and longer distance. And then last but not least is the overall cost of the solution itself as well. So again, I welcome everybody to stop by the onsemi booth and check it out, or the IDS booth there. They have it on display as well. And I thank everybody for your time.
Thank you very much, Steve.
Yep. Do we have any time for questions?
Yeah, great talk. Definitely interesting. Not the worst talk at the end of the session, definitely.
Okay.
Any questions? Allow me one question. Is it already available? Can we get it?
Yes, absolutely.
In volumes?
Sorry?
Can we get this sensor already? Is it
can
available?
you get the sensor already? Sorry, I didn't hear you. Yeah, so actually, the sensor is available, as I'd mentioned. Actually, IDS is got it over at their booth. A lot of our customers are working with it. The demand is extremely high because of what I mentioned, right? We removed a lot of limitations. So please feel free to stop by the booth, drop your information. We'd love to give you a demo. We'd love to give you more info. And we'll be in production in this by March of next year. So we've already put it through its paces. It's now going through the qualification cycle. And you'll start to see products hitting the market with this probably in the next, I would say, 6 months.